Hi, this is Kevin Buzzard, and this is the solutions to section 9 of sheet 2, section 9 of my Formalising Mathematics 2022 course. And this is about a structure called an equiv. An equiv is, if you like, it's a constructive bijection between two types. It's a function with a two-sided inverse. So to make an equiv, you have to give four things. Let me just delete this completely and show you how I do these things. To make an equiv, you have to give four pieces of information. So what's going on here, and this example, this is in Lean already. It's called equiv.sim, but let's construct it ourselves. Here we've got a bijection from x to y. In this, I mean, it's more than a bijection. It's a function with a two-sided inverse. A function and an inverse function, and a proof that they're inverse to each other. And we've got to prove that y bijects with x. And the way I made this sheet is, you start with an underscore. You see, the one thing you don't want to do is start with begin, sorry, end. Because why don't you want to do that? Because the goal now is y is equiv to x. And if I click on that, you see it says it's got type. That's bad, right? Tactic mode is for proving theorems. And this is data. This goal here is data. It has type. It doesn't have type prop. And so we shouldn't really be using tactic mode at this point. But you can put an underscore, and then this light bulb appears. And if you click on the light bulb, you can't see this, but I've just got a list of options of things that we can do now. And for some reason, it doesn't show up in the stream. I don't really understand why. And the last but one option is generate a skeleton for the structure under construction. If I click on that, then this happens. And now you can see more clearly what's going on. The idea is that we have to, you see, I explain what an equiv is over here. To give a term of type x equiv y, or equiv xy, you have to give a function from x to y and a function from y to x, and then two proofs, proofs that they're two-sided inverses of each other. So what we have here is we have E an equivalence between x and y, and we want an equivalence between y and x. So the first thing we need is a function from y to x. And again, you see, you can't begin, sorry, end. You shouldn't do this. I'm going to delete this. We've got to define a function from y to x. So we could like get intro y. That's fine, right? There. But now our goal is x, right? And again, x is a type. You see, that's not. You shouldn't be in tactic mode if your goals aren't proofs. I mean, that's a sort of a rule of thumb. So we need to get a function from x to. I mean, we may as well stay in tactic mode. Look, we need to get a function from y to x. But you see, we've got this e, and that's this equiv from x to y. If we do cases on e, we'll see what it is. You see, e is actually to get it. There's no e anymore, right? E has disappeared. It's turned into four things. And there's e to fun, which is from x to y. E in fun, which is from y to x. And then two proofs that these things are inverses of each other. So that gives us the clue, really, that because we have e already, maybe we should use e dot. I guess e dot to fun is a function from x to y. So we want e dot in fun, and that's the function from y to x. And similarly, the inverse function, that's going to be e dot to fun, right? There. And now we've got to prove. that e dot in fun is a left inverse of e dot to fun, but that's syntactically the same as saying that e dot to fun is a right inverse of e dot in fun. So this should be e dot right in. There. I mean, if you could, this is now, I should say that, right? We could. This is okay to do in tactic mode. There. If I look at, you see that this goal we have to prove that this thing is a function dot left inverse. You see, this is a prop now. That's a good thing. And yeah, the goal is slightly weird. It's function dot left inverse, but we could just unfold it probably. Function dot left inverse. You see, it says for all things for all x in y. You should say for all y in y really. So for all x in y. If you do e dot in fun and then e dot to fun, then you get back to where you started. So as I say, that's exactly the proof. That's exactly e dot right in. And as I say, you don't actually need to go into tactic mode for this as well. Begin end takes you from term mode into tactic mode, and exact takes you from tactic mode back into term mode. So really, the begin and the exact and the end just cancel each other out. So I could do e.left_inv here. And there we go, that's done that one. So equiv.trans, what are we doing here? We've got a bijection between x and y and a bijection between y and z, and we need a bijection between x and z. So that would be lambda x, and then I guess we want to do exy dot to fun x. That's an element of y, and so we want to apply eyz dot to fun of that. So once I've spelt it right, there you go, that's compiled. Got no errors, you see, that's how I know. So that's that function. Or alternatively, we could just compose them. We could just write. I mean, let's leave it like that. I think the lambdas is better. And this is lambda z, and now I need to get an element of x, and that would be. How am I going to get that? It would be ex. Let me just show you something. You don't actually need to put the to fun. Eyz of z. You do. It's imfun. Yeah, unfortunately, you do need to put them because they're going the other way. Dot imfun. You need to put something anyway. So there we go. And now I've got to prove these things are inverse bijections. So let's intro x, and let's desimp that mess there, and there we go. The desimp. Oh, that's interesting. That it does use that terminology. Oh, that's a slight blow, because that means that this question is perhaps slightly too hard for you because I haven't told you the correct rewrites. Oh, curses. So the way to do this, I mean, I need to use the fact, you see, I could do, that's a shame. There you go. I should have checked this before I uploaded it. What is this goal? It says exy. I may as well just tell you now while I'm here. Exy dot infun of, what was it again? Let's just let's pin it for a second. It says exy.infun of eyz.infun of eyz.tofun of exy.tofun of x equals x. There. You see that change has worked. So the thing I've pinned and the current tactic state, these are definitionally equivalent. So what's going on is that there's a shortcut. There's a coercion from equivalences to functions. So you see exy with a little weird arrow by it, and exy dot to fun. These are definitionally the same. So I don't actually need to put that to fun there, and I don't need to put that to fun there either. There. Do you know what I can do? I could do desimp only. Great, now we're back on track. Now I don't need to do the change. So the simplifier was changing. The simplifier, the preferred form for these functions is using that coercion to function instead of the to-fun and the im-fun. But anyway, I've got eyz im-fun of eyz to-fun. Those should cancel out. So that should be rewrite eyz.left_inv, I should think. Yes. And similarly, these things should cancel out. Well, this is now probably exact. I mean, I may as well, when I rewrite it here, exy.left_inv, left_inv. There we go, that does it. And similarly here, this is going to be intro y, intro z, desimp only, and then rewrite these things here, but rewrite the right-ims. Oh, that might be in the wrong order. Does it? Yeah, you see, it doesn't work because I need to rewrite that one first, I think. Try that. Now I've got a syntax error. Now let's try that. Bingo. Okay, that was hairier than it could have been. Apologies for that if you tried to do that and got totally confused by everything. So there you go. It's in fact it's called equiv-trans. It's there already, and there it is again using dot notation. So let's see if we can do this one. Let's get rid of the sorry. Let's put an underscore. So here we've got A is equivalent to X. We've got Euclid's version of transitivity. Two things that are equal to a third thing are equal to each other. That's one of his, he says that at the very beginning of his elements. So what are we going to do now? I want to prove this by transitivity. So this is like equiv.trans something something. It didn't like that. Oh, because it can't guess. What's the goal? A is equivalent to B. So we could put EAX here. There. Yeah, and now it says, now you need to give me a proof that X is equivalent to B. Well, it's not a proof, it's data. Now you need to give me a term of type X equiv B. But we have a term of type B equiv X. So we could do this, equiv.sim EBX. And that should do it. So there we go, the error is gone. And now we could use dot notation, of course. So instead of the brackets, we could use a $sign. You Haskell fans would know, that's function application, but very low priority. So it knows that this is a function. It wants to apply it to what's after here, but it's got very low priority, so it does everything else first. Functions normally eat the next thing they see, but if you put the $sign, then they don't do that. They wait until you've finished and then eat everything in one go. Equiv.sim EBX, we could just put EBX.sim. That's the same thing. There, now we don't need the dollar anymore. And similarly, equiv.trans EAX something something something, we could just do EAX.trans this. So there you go, that would be somehow quite a short way of doing that example. Now what have we got left? So let's make a bijection from the rationals to the rationals, and let's not use the identity function. Let's use the function to go one way. Let's use the function that sends x to 3x plus 4. So the other way, we'll need the function that sends y to, what's the inverse of this function? This is y minus 4 over 3, right? And now we've got to prove that these are left inverses of each other. So let's tidy up. Dsimp. We need to do an intro. Let's do intro x. And now let's tidy up. See if the simplifier can do it. Oh, not quite. The simplifier's had a good go. It's cancelled the 4s, but it couldn't finish it. But the ring tactic will do that. And similarly here, let's do intro y. If we do dsimp, then we'll see the 4. There we go. There's the 4s. How does the simplifier? Yeah, the simplifier doesn't do that one. And now we just do ring again, right? There. So that's the proof that y minus 4 over 3. It's sort of interesting, isn't it? I made y minus 4 over 3 by looking at 3x plus 4, thinking, well, let that be y. And now if that's y, then how do I make x? And so obviously you take away 4 and you divide by 3. And so in my head, I kind of constructed this function to make sure it was a one-sided inverse by definition. Maybe that was the one that the simplifier did. Yeah. That's the one that's kind of obvious, right? Because look, we've added 4 and then we take away 4. So they cancel and we get 3x and then we just divide by 3. So that's sort of very, it's a shame that the simplifier can't quite finish it. I guess the simplifier doesn't know that 3 is not 0. So it can't, in some rings 3 is 0. This way is somehow simpler than this way because, so what happened here? Anyway, I see. So it's somehow the fact that, there's something that I don't quite understand happening there, but it's not really the point of this lecture. Let's see if we can do this one. This video. Right, I've got to prove that, so I'm just stressing that x is equiv to y has got type, you see. This equiv is not, it looks like an equivalence relation, but it isn't because it's data. But if we define r of x, y to be the statement that there exists a bijection between x and y, then it's not so difficult to prove that that's an equivalence relation. You see, this should be a prop. Yeah, this is a prop. So how do we do that? We need to prove it's reflexive, symmetric, and transitive. So we could do refine underscore underscore underscore. There. Now we should have 3 goals. We do. So let's give ourselves 3 goals. Oops. There we go. And the first goal, we've got to prove that R is reflexive. So what does that say? Let's unfold reflexive. Let's see what's happening. We've got to prove for all x, R, x, x. Aha. So we should be doing intro x. No, intro capital X. And we've got to prove that, now we could do unfold R. So now this is an exists goal. So there exists a bijection between x and itself, and so we can use we can use equiv.refl, right? Equiv.refl, does that take something? Equiv.refl, it wants, there's a round bracket, so it's equiv.refl x. There we go. And it's finished the job for us. And now what's going on here? Why is this symmetric? So we could do intros. What do we do? X and Y, are they going to be a thing? Yeah, X and Y, and then H. But I don't want to intro H because R isn't exist. So I could do pointy brackets, E, H, E. What about that? I don't know how to do intros. There. And now E is the equiv from X to Y. And so we could use E.sim. That would work. And there we go. Obviously, the moment you use it, it solves the goal because the goal is true. And now transitive. So let's do intros again. X, Y, Z. Am I on the right lines? I am. There, and then we could do E, X, Y, comma. I don't even care. And then E, Y, Z, comma. I don't even care. And now I've got to prove. So now we could use. What would it be called? Use exy.trans EYZ, I guess. There we go. And we've proved, and it's an equivalence relation. And so that's the end of this video. Thank you very much for watching.